So I thought that today I'd go ahead and show a simpler PCB layout than I had done in the pedal design series, because that circuit for the ping pong delay was a little bit bigger and a little bit more complex than what really would allow me to do a nice step-by-step walkthrough of PCB design. So I've got this very simple overdrive design here that I'm going to lay out today. And you see the schematic here. And just a couple of things to point out. We have several ground connections here. We have pads for our LED, and we're just going to leave this switch as pads also. And so we're ready to start laying this PCB out, but before we do, there are a few constraints that we have to take into account. Those constraints are the enclosure size, the control layout, and the enclosure layout. So how the switches and jacks and everything are going to go inside. I have here the data sheet for a Hammond 1590B, which is the size of enclosure that I'll be designing this for. You can see here that the minimum inside width is 2.183 inches. So I'm going to make my width be just an even 2 inches, since I'm not going to be hurting for board space. And then the inside length is 4.215 inches. And the jacks are going to be side mounted, including the DC jack. The foot switch is going to be at the bottom. So I'm going to leave about 3/4 of an inch for the foot switch and about 3/4 of an inch for the input and output jacks. And the DC jack can go in the space off to one side of the switch. So really there's about 1.5 inches of space that I can't use. But to give a little more flexibility for where things can be placed, I think I'm just going to shoot for a square 2-inch by 2-inch PCB. There's only 2 controls in my schematic. I've got a drive control and a volume control. So I've got a lot of flexibility there. It's just the 2 controls are going to be at the top of the enclosure in kind of the normal fashion. So this is what my blank PCB looks like inside of Eagle. This is the maximum board size that the free version of Eagle will allow me to do. And so what I'm going to do is move the boundaries of my board so that it is 2 inches by 2 inches. So this is 2 inches wide. You can look at the coordinates up here to help you with sizing. So we went to 2,000 mils wide, and we're going to drag this down until it's 2,000 mils tall. And that's the size of the PCB that we have to work with. Now, the next thing that I'm going to do is I am going to, on the bottom layer, this is going to be a 2-layer PCB, I'm going to create a polygon. And what this polygon will let me do is it will allow me to assign a signal to it on the layer that I have specified, so that anytime that signal touches that layer, it just automatically works. And my analog ground is the signal that I'm going to be using. You can see that right now it doesn't look like much. If I hit rat's nest, it will show, well, when I actually have something on here, it will actually fill in what the bottom layer will look like. So now I've got the outline of my board. I've assigned the bottom layer to be my ground plane, which we can still run signals through. We just need to make sure that there's always enough electrical connection for grounds to happen. Now it's going to be time to start placing everything where it needs to go. Because of how this board is going inside of the enclosure, the top of the potentiometers needs to not exceed the top of the PCB. And also, because this is going to go right up at the top of the enclosure, we're going to want to clip these corners so that they don't um, interfere with where the screws mount. So I'm just going to come in here with this is the miter tool. Oh, come on. We click and drag to give ourselves a good miter. I'm not sure if that's even. Let's look. Yeah, it looks pretty even. So we'll just do that. Actually, I think this one is off by just a little bit. Hey, come back here. Okay. So we're going to do that. And now we're going to start placing our controls where we want them, and then we'll start placing our solder pads. So we're going to move. This is our drive control. I'm going to go ahead and put drive over here. And I will put volume over here. And this gives us a spacing between the two pots of, let's see, that is 450 to 1550. That's 1.1 inches. That's great. That'll allow for a reasonably large size of knob if so desired. And now we start putting in our solder pads. Normally I would put my 9-volt and ground pads up here because the DC jack usually comes through the top for me, but because the DC jack is coming in from the side, specifically from the output side, we're going to want to put our 9-volt and ground pads right here. So we're going to grab 9 volts. And we're going to grab, this is a second 9-volt connection. This is just for being able to connect a battery tab. We've got ground that's going to come in here, and we're going to have a second ground for the battery tab or for the battery snap. And then we hit rat's nest, and now it shows us everywhere that our ground plane exists on that back layer. Okay, now we're going to put our input. Because we're looking at the bottom of the board, this is as if we're looking at the bottom of the enclosure. So the inside is the input side is over here, the output side is over here. So we'll put the ground connection for input right over here in the corner. And we'll move this. So in and out, these guys are both going to get mounted or wired up to the stomp switch. So that being the case, I'm going to have a string of 3 grounds. I may as well put them all together over here. So we'll actually have 9 volts go like this. Looks like these are going to need to come up a little bit. Beautiful. So there's those. Next we need some pads for the LED. We'll just go ahead and stick these in the middle here. Like that. And you can see that every time I click rat's nest, the yellow lines are getting redrawn because well, they may be green, but these bright colored lines are showing what all needs to be connected together. Now, my switch is just going to be pads. It doesn't really matter where it goes, but for the sake of everything looking nice and pretty, I'm going to put it right in the middle, like that, which means that this guy's not in the middle. I like to make sure that the layouts are nice and aesthetically pleasing. um, so sometimes I'm a little particular like that. So there we go. That is all of the basic connections now. Now what we can do is start placing our components where they make sense. What do I mean by where they make sense? Well, for example, we have our current limiting resistor for our LED, and we should put him down by our LED pads. And then we also have, for example, this is a power filtering cap for the 9 volts. We have a polarity protection diode here. We're actually going to give a little more space so that we can get some nice clear labeling in here later. And let's go ahead and put that guy right there so it looks nice and pretty. Okay, so those were some of the easy things. Next, we start considering the signal path as well as what we want the board to look like. So for example, I like things to have a fairly symmetric look on the PCB. That's not always possible, but in this case, we should be able to have a reasonable look like that. So I'm going to put our transistor right in the middle, right there. This switch, if we come look over here, governs pairs of clipping diodes. So we should put our clipping diodes by our switch. And we will take this guy, and right now I'm just putting these very roughly where they will go. And we will deal with the specifics of it later. Right now, I'm just putting the parts roughly where they belong and in a way that looks nice, and then I can start, switching things around as needed. Now we'll come back over to our schematic, and the input signal is going to have R1 and C1 connected to it first. So we'll come grab R1 and put it over here by our input pad. We will take C1 and also put it by our input pad. After C1, we've got another resistor and another capacitor before going to our drive pot. Now our drive pot is over on this side for right now, but we don't necessarily want to be running our signals all the way across, so it's actually going to make a lot more sense if we move our controls around. So we're going to swap places for volume and drive. And if you think about it, looking from the front, this makes sense because on the input side you're going to have drive, on the output side you're going to have volume, and that just makes a lot of sense. So now that we have done that, we need to grab R2 and C2. Here is R2. Here is C2. And now another aesthetic concern is if we look at our resistors and capacitors here, we've got them alternating, which works well for signal flow, but it doesn't look very nice. So I'm going to group the resistors and the capacitors together, which in this case is really a simple matter. We'll just go like this, and we will go like this, and we will take this guy and flip him around, so that now if I come in here and look at what I need to do, my input will come to here and to here. This guy will get connected around over to here, this guy will get connected to there, and this will end up coming up to my drive pot. Okay. Now after the drive pot, we need C3, R3, R4, and C4 all around the transistor. So let's grab R3, C3, R4, and C4. Whoop. And those guys will kind of go there. And because we have our diode and our cap over here, I'm actually going to orient them so that they sort of mimic what's going on over here with my resistors and capacitors. In fact, if I put this guy kind of like that, and like that, give that a little shift, then I can take R5 and C5, which are on the output side of everything, and I can bring them down so they look something kind of like this. I'm going to switch that up, and we rat's nest. And there we go. I'm going to save right now just so I don't lose any of this progress. And now we have things roughly in place. Now it's time to kind of put things more where we may want them. So, I'm pretty happy with how things are over here. I'm happy with our diodes, except for the fact that I think I will just squeeze the diodes in a little closer here so that this guy can come up, because if we look, this is at 200 mils from the bottom and this is at 250 from the bottom, and so that kind of ruins our symmetry look. So we'll go like that, and now we have things that are kind of mimicking each other, being the same level all the way across here at the bottom. And then let's go ahead and let's do a pair of resistor capacitor and a pair of resistor capacitor side by side up here, which I can do by taking this resistor, needs to kind of come over here somewhere, and this capacitor comes over here, and this resistor can kind of come over here somewhere, and the capacitor over here. And so this is our basic look. Let's go ahead and zoom out. That looks just fine, nothing is cramped. And so the final thing to do is we want to make sure that with these diodes here, that we have the right pairs of diodes with each other. You see that this diode connects over onto this side, and this diode connects over onto this side. So we're going to trade places here. We're just going to get him out of the way, bring this guy over. That's going to go like this. And then we're going to flip this guy around so that when we rat's nest, you can see that this guy connects to this guy, connects to this guy, and this guy connects to this guy, connects to this guy, and the center lug comes up over here to our volume connection. Okay. Let's take a look over here, make sure that this all makes sense. That looks good. All right. So now we're ready to begin actually connecting our traces. So I'm going to try and keep as much of my signal on my top layer as possible. And I generally use a 10 mil trace width for signal. It's not giving me an issue yet. And so we are just going to begin doing the easy stuff. Okay, the stuff that makes a lot of sense is where we're going to start. And so this all makes a lot of sense because the signal flow is all pretty clearly defined through this part of the circuit. And let's see. Yeah, let's go ahead and do that. We'll take this guy over to here. Now you see I've got two crossing lines here. That means that I'm going to have to come up with a way to make sure that they don't cross. The way I'm going to do that is I'm going to take this guy down around the other side so that he can kind of loop under, if you will, just like that. And then this guy can just come over like this so that it can then come up to these other components, and that's really nice and easy. This is also pretty straightforward there. Now let's go ahead and wire in these diodes to our switch. Because these are just clipping diodes and I have a ground plane on the back, the other ends are just going to connect to the solder pads that are through plated anyway. And so it's really nice and easy that way. We'll connect that there. And since this is 9 volts, actually, so when I do power, I like to actually use a wider trace width for power just in case something needs a lot of current, just in case something is going to draw a lot of current. In this circuit, nothing's going to draw a lot of current, but for the sake of sticking with how I typically do things, we're going to do 20 mil trace widths for power. So we'll come over here to our 9 volt pads, connect them together and connect them to our polarity protection diode. The other side of the polarity protection is going to go like that. Now the LED is not going to take much current at all, so it doesn't need a big fat trace. So we can actually go like this. There is our polarity protection diode, and now we'll come from our volume pot. I'm actually going to bring this guy around instead of going between the legs on this filtering capacitor. I'm going to go around just so that I've got plenty of clearance. I mean, there's no reason for me to have really cramped traces or component placement in this circuit. And so if you can space things out, you run lower risk of there being any interference between signals on different lines. Okay, so there we go. We now have all of our circuit traced through here. To check that, we're going to come up to Tools and DRC. This is the Design Rule Checker. And you can specify all the different design rules that you want your PCB to have. For example, this spacing between different signals, I like to have 10 mils of spacing between different signals instead of the default 6. And then what will happen is after I apply and check, it'll go through and make sure that everything meets that requirement. Also, on masks, I like to set the limit here to 15 mils so that it will mask anything smaller than that. That means that if I had any vias going from the top side of the board to the bottom, it would actually mask the vias so you couldn't accidentally solder them. So we're going to apply those, and now we will check, and it says I now have one clearance error, something that does not meet the design rules that I specified, and you can see that we're just a tiny bit too close right here. So there are a couple of easy ways to fix this. The easiest way, move this out of the way, the easiest way is to just come and route a new trace between the 2 points, and it will now place it such that it meets that. You can see that it automatically cleared. There are 0 errors now, which means that from the standpoint of all of my traces here, they all match up with what I have specified in my schematic, meaning all the components are connected according to the way that my schematic outlines them. So there's our PCB. Now I am going to turn off the top values layer. I don't want to see it because we may change some circuit values later or some component values later, and we don't necessarily want to have the PCB no longer be valid just because we put in specific component values. Now we will go in and we will put all of our labels for all of our components in such a way that everything looks nice and pretty. And I like to try and be relatively consistent with where labels are placed relative to the component. So I'm going to place all of my capacitor labels to the inside of the components, and I'm going to put all of the resistor numbers on the footprint. And so it's just a matter of working through the board, placing these things where we want them. This diode, he's going to come over here so that all of this room is for these labels. Capacitor. Now, these diodes, I'm just going to have them sit top and bottom of their respective diodes so that we're not clogging up in here with labels, and we could put them here on the outside, but it's not really necessary. Now this switch label right here doesn't really need to be there. We could just delete it and be rid of it, but it's not harming anything, so I'll leave it there. Our transistor. If you want to find place things, at least in Eagle, after you have clicked move, you can then hold down alternate, which uses a much finer grid spacing for placing anything, components, labels, you name it. Okay, let's see, do we have any other labels for components? No. Okay, so now we can place our labels for our different solder pads. I just like to make sure that they are centered over their pads and everything. You know what? Let's actually do these centered on the side of their pads so that I don't have any conflict going up over here. For the LED, what I'm actually going to do is, you see I've got one marked LED plus and one marked LED minus, but having those right next to each other is a lot of label. So I'm actually going to go to my top names layer. I'm going to add text, and this is going to be plus LED minus, which is going to indicate that these are my LED pads, and plus is on one side and minus is on the other. So I can delete these individual labels like this. I'm going to pull the properties up, and I'm going to bring this size down so that it matches all of my other labels. And I'll put it right there like that. That means we have the positive and the negative leg. Now, because I have 3 different ground pads all right here, I don't need to specify that they're each different grounds. Rather, I just need to specify that they are all ground. So I'm going to put this ground in the middle of these 3 pads like this. 9 volts is going to be the same thing like that, and we will get rid of that 9-volt pad there. And now, as we look at it, that is a very neat and tidy board. So I've just saved it, and then what we'll do is, for the final thing, we'll put in another text box, and this is going to be just telling us what the circuit is and the revision. So this is the JPOD. It is revision 1.0. And then if you want, you can put copyright information in here, because a PCB layout does fall under the category of protected artwork for at least US copyright laws. So if you're worried about someone stealing the artwork for your circuit, you can also put that in there. But I'm not overly worried about it for this one. We'll just put it right up there, loud and proud. And with that, we now have a complete PCB. And to prepare to, now that we have this PCB laid out, to prepare it to be sent off to a board manufacturing house, we come up here to the CAM processor where we will generate Gerber files. And we can give it a CAM job template or a CAM file template. So I have two different ways of generating these CAM files. This one right here for JLC PCB, you can actually download this from the internet, which is all I've done. And that is the standard board or the standard CAM profile for what JLC PCB wants to see, which is Gerber files and Exelon drill files. I have modified it so that it doesn't even look at the values silk screen for the top layer. So I'm going to choose that one. What'll happen is now it shows me all the different layers that are going to go into the Gerber file. It tells me that I'm going to create an Exelon drill file, and it's going to export it as a zip file. So I click process job, the window comes up, it automatically gives it a name. I'm going to call it JPOD_1P0 for 1.0 or 1.0. We click save, it thinks for half a second, and it has processed successfully. So now what we can do if we like is we can, oops, display one off there. Now what we can do is we can go off to, let me bring a, come on, trying to bring a web browser window up here. There we go. And let's just go to jlcpcb.com. We click on their instant quote button, and we're going to add Gerber file. We're going to go off to where I have all of these things kept. Eagle projects, JPOD, and here's our zip file. We open this, it's going to load it up, and if it successfully loads up, then it is a board that they can make. So it's showing us our two layers. Our top layer, it shows the silk screen and the routing and the pads and everything. Bottom layer, same thing. All of this kind of lighter color indicates that that's all copper. The darker color is where the copper is either etched away or processed away by whatever process they use. So this is a board that we can successfully send off to JLC PCB. It could also be sent to a service like PCBWay or OshPark. And with that, you can just pick what you want and order your boards. We'll go ahead and close this window down, and there we have it. We now have a successful, simple PCB from our schematic for this overdrive. I hope you found this useful. If so, I invite you to go ahead and like and subscribe, and we'll catch you next time. Thanks.